The atomic physics experiment is one of the most interesting because it relates directly to the quantum mechanics you've been learning in class. The problem is that if you were around when it was being developed in the early part of this century, you would understand all the notation and all the peculiarities of how things developed. Nowadays, the mathematics is sophisticated. They've cut away a lot of the early material, but in the meantime, they've made it difficult to get started. So when you begin this experiment, you probably have to do some reading. And one of the good places to start is in this little book by Hertzberg. It was written actually 60 years ago, but is still as good today as it was then for just getting a background, an appreciation of the notation, how the field developed. This is listed in your references together with another book by Professor White, but if I have a new spectrum that I need to look at and don't know where to begin, this is a fairly good place. Very low level, you don't take the quantum mechanics in it, but the ideas are all here. When you want to take the next step and find out about data, where can you find the latest numbers that are valuable? Because if you're doing it in a modern experiment, you want to know where to start. Then there's a book here published by the National Bureau of Standards, now called the National Institute of Science and Technology. And they keep all spectroscopic data right up to date. This is one of the older volumes, but it is at least typical of what you can expect. So anything that's known about an atom and its structure is going to be in these. And you can see largely tables, but there's one for each atom. It is kept, as I say, up to date. You can call the Bureau and even get today's latest thing like you would a racing quote or a betting quote. You would find all the data you need. Now, let me begin by saying we need to learn some language that goes with this experiment. And that has to do with how do we label things? What names do we give? Because as you go read a book, they will put up these numbers, these symbols, and you'll wonder, where did they come from? So let me tell you how it gets started. First of all, in any atom, we have the extranuclear electrons. Each electron has quantum numbers associated with it. And there are 4 of them. N, L, J, M, sometimes M sub J. That's like the names. Each electron has got 4 names. You can also have a different set of 4. Like your parents will probably give you nicknames. Well, there's a different set. N, L, M sub L, M sub S. Those 4 quantum numbers, every electron in an atom has a set of those. And you remember the Pauli principle says only one atom can have a set of a distinct set of these. No 2 can have the same set. And that describes what happens. Now, what else do we think about for notation? Well, atoms are characterized by 2 things. Their energy levels and the wave functions. These are coupled together, as you know from your quantum mechanics course. But when we do the experiment, we don't really care so much about these because they aren't measurable in the usual sense. What is measurable is the energy. So what we need to learn is the notation that relates to the electrons and their names and the energy levels. And we have that, then we can begin to read with understanding some of the texts, and you have kind of the context in which things go. Now I'm going to tell you some of the conventions without telling you all the reasons why it comes out this way. I'll just say that's the way it is. N is the principal quantum number. Roughly speaking, it refers to the gross energy of that electron. Not exactly because they're interactions, but that's the way it starts. N is associated also with shells. That's a more chemical term, more often used in chemistry. But they have shells of atoms, and it's K, L, M, so forth, for 1, 2, 3. And mostly physicists will talk without using those. All of a sudden you get somebody in X-rays and he says, well, you knock an electron out of the K shell. Well, you want to remember where that came from and not be just surprised. L is related to the angular momentum. In this case, it's often called orbital angular momentum. We don't often use that term. We just say angular momentum, but I will call it orbital. And that comes about because of the early picture of a nucleus and an electron tearing around the nucleus. As you would a planetary system, that's an orbit, and you can assign an angular momentum, an orbital angular momentum, to that electron in its position around the atom. Now, you know, from quantum mechanics, it comes out naturally from the mathematics. You may want to go back and see how it does that, then come here and look at this more practical phenomenological picture. Then, in our designation here, we have J and M sub J. It's easier to say, let's talk about M sub L and M sub S first. M sub L is the projection of L on the z-axis. Now you say, well, what's the z-axis? Well, you just set it up. Anytime you look at it, you're setting up an axis, and if you try to make a measurement, there's an axis. We will say that's the projection on the axis, and that simply says if this is the axis and it's going around like this, you have no projection of L on the axis. If it's going around like this, you have some projection, and from your classwork you know that it's quantized and those things, and that goes from minus L plus 1 up to plus L. And I should say that L goes up to n minus 1, but we will come to that in a minute. Then there is another thing, M sub S. Well, there is a number called S, and this is the spin of the electron, and it's 1/2. The quantum number is always 1/2. And that can be either along the axis or parallel, anti-parallel to the axis, so M sub S is equal to plus or minus 1/2, and it's the projection of S on the z-axis. Now, there's still one other concern, which if you've gone farther in theory, you'll remember that there is the total angular momentum J, and that's L plus S. And because they are vectors, this is a vector coupling model, and sometimes we will just put a vector over there, but it's restricted by the fact that all of these have to be either integers or half integers, and we will come to that in a minute. So now, if we look up here to these four numbers which we've spoken about, principal quantum number, orbital angular momentum quantum number, total angular momentum quantum number, projection of total angular momentum on the z-axis, or principal, orbital, projection of the orbital on the z-axis, projection of the spin on the z-axis. Either set of numbers can be used. Most often, but not always, most often this is used, and the Balmer series part of the experiment uses that. The second part of the experiment, the Zeman Effect, uses this, and we will expect them interchangeably to be useful to us. All right, now we want to talk a little more about these quantum numbers, how they're used to characterize a particular atom. We assume that every electron in an atom has a set of quantum numbers that is unique. And we assume that those don't change even though there are interactions with other electrons. It's just an assumption, and it seems to work very well. When we talk about these, when L is equal to 0 for an electron, we say we have an S electron. It's another piece of lore that grew up with the field. When it's equal to 1, we have a P electron. And when it's equal to 2, we have a D electron, and so forth. The next one happens to be F, and then G, and so forth. So many times when people refer to the electrons in an atom, they will say this part, not the angular momentum, and assume you fill in the rest. This is important because in most experiments, when you have an atom in its unexcited state, it has all the electrons settled down, the energy is the lowest, and that's fine. When you excite it, a single electron gets excited, only one. And so that's called the optical electron, and it has these quantum numbers, and then you can describe the energy to which it's raised in terms of these quantum numbers and another set of notation. So let's look at an optical electron and what happens. Let's assume it is down here, and it will be in an S state. That's 0. But you say, how far down? Let's call it n equals 1. And you say, this electron, but this atom, because only one gets excited, you pick one of those electrons that's called the optical electron, and I'll show you which one, and it can be in the 1s state. That means n equals 1, L equals 0. If we excite it, you draw another energy level, and you could put it here, let's say, at the 2p level. Now that means put some energy in, a fair amount, goes from n equals 1 to 2. The angular momentum goes from 0 to 1. We like to have another way of designating this state when we get to more and more complex atoms. And how do we do it? We have another notation that goes like this. We have something that reads 2s plus 1 L J. The spin in a one electron atom, in this case, is 2 times 1/2 plus 1. So that either of these states would have a super 2 up here. The angular momentum, we have a different label for that. If angular momentum is 0, we have an S electron. We put a big S now, a capital S here. And here, the angular momentum is 1. It is a P state. Down here is the total angular momentum. When you have an S state, it has 0 angular momentum, 0 orbital angular momentum, so it's an S state. J is L plus S. S is 1/2, so it is a 1/2 down here. And this is called a doublet S 1/2 state. And when you see that, you don't have to know what produced it. You just say, well, it's a multiplicity of 2. That's a spin 1/2 state. It has 0 orbital angular momentum, and it has a total angular momentum of 1/2 due to the spin. And so this is called a doublet S 1/2 state, and this is spectroscopic notation. Many, many people don't teach this in a class. Wait till you take the graduate record exam. One year, there were 2 questions about spectroscopic notation. One of our best students, best undergraduate students, had not had this in class, did not know this, and got knocked down another 10 percentile points on her exam simply because she didn't know this. a triviality, but it's important. It's like not knowing somebody's name, not knowing the name of your professor. So when you address the atom, there's the name of that level. Now, in this case, it's a p state, and from our designation that the J is equal to L plus S, this can be two states here, 1/2 or 3/2. Now, as you go further and further into the theory, you will see that in most cases, these are not degenerate. They have different energies, and you will have a second state here. But that's down the line. The first thing is to learn the names and how do we get started on it. Now, suppose I give you a complex atom like mercury or gold or any of the rare earths. You say, I'm lost. But it is usually a single electron that's the optical electron. You focus on that. Maybe it's 2 or 3, but start out with a single one. Then all these symbols over here become capital letters instead of small letters. These stay exactly the same, and you can open it up and look at mercury or gold or tantalum or thallium or platinum or rare earths, and the meanings are all the same. Now, sometimes in the earlier books, the techniques of the descriptions were not well developed, so you'll see some older notation, particularly when you go to look up neon, let's say for the helium neon laser. But those are all things you can cope with if you know these basic ideas. So now what we want to do in our experiment is take this and look at the energy levels of hydrogen. And here's how we're going to do it. Now we're going to expand our picture here. I only have 2 energy levels. Let's look at hydrogen and what the energy levels of hydrogen, how the energy levels of hydrogen are distributed, and what kind of an experiment we might do. We have to develop another way of describing energy also. We need a 0 point. You remember, any time you discuss energy, you have to have a reference point. Well, in spectroscopy, the reference point is always taken as the ionization energy of the atom. We take that optical electron we've spoken about, snatch it away to infinity, and say that's 0 energy. So we put a line up here, and this is 0, and this is energy. And in hydrogen, we have a single electron. I had it down here in a 1s state, so the lowest energy level is the 1s state of hydrogen. And it has a spectroscopic notation of doublet S 1/2. We want to fill up the energy levels. Well, you remember from your elementary theory that they go as 1 over n squared. So if this is the lowest energy level, the next one is 1/4 this distance from here to here. So here is the next energy level. This is a 2s level. And you see there's a big, big gap here. How big? Well, if this is 0, this is down here at minus 13.6 electron volts. And you ought to memorize this. You will find that throughout your career as being one of the numbers you need to know. It's just as important as the speed of light is to many, many other experiments. And then the next one is 3s. It's a 1/9 of the way up. It's up here. This is 3s, and so forth. Now you're going to ask me, what about the orbital angular momentum? You can't have any here. What about here? You ought to have a 2p state. Why can't we have another 2p state here? We can, and it's there. But in hydrogen, for our purpose, the first approximation, these are degenerate. And this one has 3p, and it has 3d. But these are pretty closely degenerate. Now, as you get further along, you'll discover they aren't. But right now, this is good enough. And in hydrogen, we often just plain put n equals 1, 2, 3, 4, 5 up to infinity, and we don't talk about this part of it. So I'm going to erase it, because it doesn't help us in this experiment. Another way of saying it simply is that the resolution of the spectroscopic instruments are not great enough to tell you what's happening. All right. In our well, you see, all the rest of the levels fall up in here. With these conventions, we still have another one. When an electron makes a transition, that implies you have to excite it. We put it in a bottle and shake it and excite it. In accordance with Boltzmann's description, we excite these energy levels exponentially with the negative energy of these. And if we have an atom here, it can make a transition here. If we have one here, it can make a transition here, but it can also make one here. This line here is in the vacuum ultraviolet region of the spectrum, meaning we can't see it. They give you good sunburn. The sun radiates here, it's stopped by the atmosphere or would be burned to a crisp, and the astronauts have to look out for that. This one is in the red region of the spectrum, and as it developed historically, all the transitions made to this level, n equals 2, are called the Balmer series. So we have transitions from n equals 3 to 2, 4 to 2, 5 to 2, 6 to 2. That's the Balmer series. Now you might guess in the early days people had a field day as they were able to extend their spectroscopic observations. Everything that lands on this level belongs to another man's name. Everything on this level to another man's name, and they get farther and farther into the infrared. And finally people gave up as detectors got better and they quit assigning names to them. This is the part that we're going to measure in hydrogen. And this will constitute the Balmer series. We fit the curve, we determine the energies, and we see how well it's described by the simple theory, Bohr theory, or quantum mechanics, and how close it comes. It's not quite a show and tell. It requires some statistical analysis. You can use what you've learned in the error analysis laboratory in processing the data. And it's marvelous to see. You can see these with your eye. It all comes out right. It's one of those experiments that says, yes, quantum mechanics really does work. Now we're going to extend what we've done to another atom, helium, because it has some different properties because it has 2 electrons instead of 1. Let's draw a picture of what an energy level diagram of helium might look like. It will have a 0 energy as before, and that occurs when you snatch 1 electron off of helium, the optical electron. It will have a ground state down here like this. It will not be the same as hydrogen. It will be different. These, of course, are the same because that's the 0 level. Now this has 2 electrons, so we call it 1s with a super 2. So n equals 1, no orbital angular momentum, 2 electrons. Sometimes you will see it written 1s, 1s. Not often, but either way. And the chemists use this notation a lot because it's unusually convenient. Now you ask the question, what happens? Well, let's excite one of the electrons like this, and this will now be 1s, 2p. We've excited 1. There's the optical electron, some energy. And then we can go up here, if we like, to 1s, 3p, and so forth, and we get transitions down here. But now you remember that I mentioned spectroscopic notation, and that was 2s plus 1 Lj. And now I'm using capital letters simply because we have more than 1 electron. Now, in the ground state, remembering the Pauli principle, that you can't have two electrons with the same sets, they're both in L equals 0. They both will have a spin. they must be oppositely directed, so together they couple to be 0. So for the ground state, S is 0. This is an S state, it's 0. This is 0, so that is a singlet S0 state. Simple as that. What's this? This is a singlet P state, singlet P1. Now, I'm not trying to explain all these to you or make you feel comfortable. What I'm really trying to do is say, now you know what you're looking for. These are like waymarks. Go read about them until you feel comfortable with being able to produce these. And any of the older texts will have all kinds of examples like this. And when you read a current paper on nuclear magnetic resonance or optical pumping or lasers, they'll use all these numbers, and you'll be lost if you don't take the time to go and have a look at them. Now, just for our information, remember that if we have two orbital angular momenta different, we can now align the spins. So there is another complete state if the spins are aligned. This is a 1, and this becomes 2 plus 1 is 3. So there's a whole set over here of triplet states. And these are separated usually in a text. And we have triplet energy levels. So these are called triplets because there's an upper 3, and these are called singlets because there is an upper 1. Now, you can see that's going to modify, because of quantum mechanics, what the energy level structure looks like. Here, these were all degenerate, so I said we didn't have to worry about those states, and there's only one value of spin, and the orbital angular momentum doesn't do much. It's just a simple Coulomb problem, almost like a planetary problem, except for the subtleties of quantum mechanics. But over here, we have many more subtleties. We have twice as many, simply because we have singlets and triplets, plus all the other possible combinations. Now, what does that do for you? Well, first, it makes the spectrum complicated, so we don't look at helium to get any measurement directly, because it doesn't tell us something nice like the Balmer series. This marches along like soldiers, and you see them. This does not. It's a more complicated thing. But there's something we can do with this which we cannot do with hydrogen. We can put a magnetic field on the atom. See, if you have a nucleus and the electron is going around, when you put a magnetic field, this is a charged particle, it's a current, it has a magnetic moment, you put on a field, it changes the direction, and the energy changes. And the energy changes in such a fashion that it goes with the magnetic moment times the magnetic field, so that there's a change in energy, or just an additional energy, a magnetic energy, which goes like this. So now the magnetic properties of the electron around the nucleus enter into mu. This is an external field, and we change the energy. So what we're going to do now is look at the levels more closely, put on a magnetic field, and watch the levels change. Now here, these are large energies. This is in the order of ballpark, so this is 13.6 electron volts. Well, this is on the same sort of magnitude. But this term is very small. And it just relates, you're taking the orbit and you're orienting it with respect to the field and seeing how much energy. In a sense, that splits the energy levels, as we call it. It changes them. So what we now do is to think about an experiment with helium in which we can do this. So I'm going to erase the triplets because that's too complex. It's accurate. I've done it, but it's too complex. We're going to do a simplified thing. You might say, well, why don't we just do it with hydrogen? Well, hydrogen is a Coulomb field. So when you put on a magnetic field, you don't do much. You don't disturb the atom. You just change that one electron. But when you have helium, you have two electrons interacting with each other. And so you not only disturb what one electron is doing, you disturb the interaction, and the effect is much bigger. It's not big enough to see here. It is big enough to see here very easily with the instruments we have in this laboratory. In a sense, it adds another term to the Hamiltonian to have two electrons, the Coulomb interaction of the electrons, which we don't have over here. And that plus this combine to give us a very nice Zeman effect, as it's called. So we observe the structure here, we observe something smaller here. Now what do? Well, we focus on one of the simplest levels possible. And this one won't split. It has no energy here. It has no total angular momentum. And so it doesn't have anything, and you can't see it when you put on a field because it has nothing to operate on. This has 1 unit of total angular momentum, and you say, well, then it's going around the thing like this if you think of planetary motion, and you can jerk it around until you reorient it and you change some energy. So we have to somehow relate this to what's actually going to happen. All right, let's look a little more at this equation and how that relates to what this does. I'll erase the Balmer series now because we've done that part of the experiment and focus on the Zeman effect. We have this term that E is mu dot B. Well, the magnetic moment depends upon what the atom is doing. And we have a constant, and we have another constant, and we have the angular momentum J and B. But we have a mu dot B like this, so this is going to be mu G M sub J times B. Now comes your quantum mechanics. It said that has to be an integer value. So we look at this and we say that means if we have a B and a couple of constants and we orient M sub J, we're going to get an energy here. So I look at this, the J is 1. What can I have? I can have M sub J 1, 0, minus 1. Just like that. So now, when you put on a field, you split an energy level. How big is this? Very small, 10 to the 5th down, roughly speaking. 10 to the 5th down. So this is huge. This is a 1 in 10 to the 5th, but it's still measurable with the instruments we have. We have to use a different one from the Balmer series, but we have something that will do that. And again, we might look at a transition like this, and after we put on the field, we might get 3 transitions. So we see a splitting of the spectral lines, as it's called. Really, we split the energy levels here. And the transitions then manifest themselves, in this case, in 3 more lines. Now, this transition happens not to be permitted, but the idea is right. I mean, a couple of these, but the idea is right. What you will need to do now when we go to the experiment itself is look up in the tables for these energy levels, which line is the one we're after, and do a trial calculation or an estimation of this. Now let me make a simpler drawing, more directly related to our experiment, because there are lots of ideas in here, and you will need to sort them out, and let me give you a little help doing that. In our experiment, we are going to look at a transition between 2 levels described as singlet D and singlet P. You will need to look up in the references books the energies of these levels, and when you do the second part with the yellow line, you'll need to look up that also, but that's included partly in the write-up. So we're going to look at this transition, which is in the red region of the spectrum. This has a total angular momentum 2, and this has a total angular momentum 1. If we go back here and refer to this equation, then this must have some value G, I'll call it G2 and G1. There. We have some fixed value of B, that's a constant. Here is a quantum number. We can have, for this level, 3 orientations. And I will draw the splitting as if it were like that. This would be m sub j equals 1, 0, and minus 1. Up above, we have j equals 2. So we will have here five levels. Now practice thinking about degeneracy. It is 2j plus 1. You've learned that in your statistics class. You've learned it in other things about degeneracy. With no magnetic field, there are 2j plus 1. That's 3 levels. Here, no magnetic field, they coincide. There are 5 levels. And when you put on a field, then the degeneracy is removed. And again, this is m sub j, 2, 1, 0, minus 1, minus 2. We are going to look at this transition to red with no field. This will also be into red, very small splitting. And we will have transitions allowed by selection rules from here to here. You will need to look up the selection rules, refer to your theory or your text or whatever, and draw the possible transitions. And I won't do that for you, except to say it is common to draw this line here like that as a spectrum line where this will, let's say, is the energy of the spectrum line, or you can put the wavelength going this way, and to draw the other lines which refer to the other transitions between these levels. And there are 2 polarizations you'll find out. There are pi and sigma. So what you will need to do is to build up this picture, what you expect to see, and when you go to the spectrometer, see what these transitions are. I could tell you more, but I think it's better if you follow it through yourself and make a picture like this, and I will ask you about that when you take your preliminary laboratory questionings.